Okay, I just figured out who's chairing the session. It's me. Right, so thanks for coming along. I will not be doing big introductions and things. I certainly haven't used ChatGPT to write any introductions, so that's good news to start things off. Right, so kicking into it straight away, we have our first speaker of the session, which is Aditi Subramanya. Welcome to the stage. That is all the introduction you get, sorry. And clapping as well.
All right, there we go. I did use ChatGPT to write my introduction. I try and use AI for as much as I can now because it's great. So, well, good morning, everyone. Thank you for having me this week and today as well at my first eResearch conference. It's been really nice to meet a lot of you. I go to the Australian version of this conference and have been for the last 7 or 8 years. And it's really nice to now skip over the pond and come to New Zealand as well and meet some really cool people. So today I would like to talk to you about the insights and how to engage about the future of eResearch and some of the practices that Pawsey takes in advancing our infrastructure. So the journey towards creating efficient, inclusive and forward-thinking eResearch environments is both challenging and exciting for us. It requires us to constantly innovate, collaborate and most importantly listen and adapt to the needs of our research communities. So in the realm of eResearch, the evolution of uptake and technology is paramount. That's how we get our work done. Researchers worldwide are harnessing cutting-edge technologies to enhance their capabilities, and Pawsey, as a leader in the field, is continuously innovating by staying abreast of these technologies, such as quantum computing, and translating these advancements into practical solutions for researchers across a range of disciplines. Sorry. So this approach has led to significant developments in our HPC capabilities, data storage and management tools, all aligning with our eResearch landscape. And so Pawsey has a commitment to advancing our infrastructure, and it's achieved through a multifaceted approach. So we embrace HPC technologies, high-performance computing technologies, that enable researchers to tackle their complex problems with unmatched computational power. And we do this by providing researchers, of course, with our infrastructure, but also access to comprehensive training, data management and storage solutions that facilitate their research. So our methods are rooted in collaboration with both our service providers and our researchers by understanding their needs and delivering tailored support. And Pawsey's tangible success is something that I will hopefully get time to show you later on through our research that is enabled by our resources. So researchers from various domains have used our supercomputing facilities and data solutions to accelerate their discoveries. From simulating the behaviour of subatomic particles, using AI for traumatic brain injuries, and predicting the impacts of climate change. So my name is Aditi. I haven't introduced you yet. This is where AI comes in. My name is Aditi. I'm the partner manager at Pawsey, and my primary goal at Pawsey is to work and consult with our communities and our partners at the centre so that we can work together to solve some of Australia's most advanced scientific research problems. So traditionally in Australia, we pay our respects to the communities whose lands we will live and work on. And so I'd like to acknowledge and pay my respects to the elders past and present of the Whadjuk people of the Noongar Nation, whose lands Pawsey is on. I also learned the other night through a few colleagues at Nessie, after a really nice dinner, that it's customary here to share your pepeha, and I hope I said that right. And so I'm proud to share mine with you today as well, after doing a little bit of reading and research. So hello, the Darling Ranges are my mountain, and the Swan is my river. I'm from India and Australia. Subramanya is my family, and my name is Aditi. So thank you for sharing that part of your culture with me and also letting me share my story with you. So a little bit about Pawsey. The Pawsey Supercomputing Centre is located in Perth in Western Australia, and you guys heard this morning that it's only hot and rainy. It's not. I want you to come to WA. It's really nice. We get really nice weather in between, so please come down. I'm trying to figure out a way to hold a conference or something there. But yes, we're located in Perth in Western Australia. We're a Tier 1 high-performance computing facility that services researchers across Australia. So the person that you saw up there before, his name is Joseph Pawsey, and he was a pioneering radio astronomer in Australia, I think back in the 50s. In 2009, the Australian government allocated about $80 million in funding to develop a petascale supercomputing facility to support the nation's astronomy efforts through the Square Kilometre Array projects and the Murchison Wide Field Array projects. And that's how Pawsey was essentially born. Since then, we've grown into a much larger and premier research facility, servicing over 40 organisations, 2,000 researchers for high-impact science such as radio astronomy, quantum computing, artificial intelligence, machine learning, bioinformatics, energy and resources, engineering, health, and climate science, and more. So that is our newest supercomputer, Cetonix. So we've been through a massive infrastructure refresh project in the last few years. In 2018, the federal government funded us with another $70 million to deploy our new infrastructure, and Cetonix is what we came up with. So it's Australia's most powerful supercomputer at the moment, but more importantly to us, and hopefully the community as well, it's Australia's greenest supercomputer, and it's 4th greenest in the world. So that was a real priority for us when we were, thanks for the clap. Yeah, we were happy with that too. We're really proud of that. It was important to us, it was important to our community, and through a lot of consultation and engagement with various stakeholders, from research to our own staff base to the vendors that we engaged with, this was really important, and our partners as well. So with investments like Cetonix and the world's first room temperature diamond-based quantum computer, which is that over there, Pawsey is able to basically support the uplift of technological advances and look into the future as well. So our mission at Pawsey is to enable science and accelerate scientific discovery in Australia. But beyond the fancy technology is our people, and I believe that that is our biggest strength. It's the people. It's our diversity of knowledge, our backgrounds, and our expertise that allow us to work with and support our large research community as well. And so when thinking about eResearch infrastructure and the longevity of it or the life cycles of it, it's the people that keep it going, kind of like what Rosie was talking about this morning as well. So for all of us in the room, why are we here today? So what are we doing with our infrastructure? So I think that our infrastructure support and services are addressing global challenges, and we're all actively doing our bit to take part in that space. So eResearch infrastructure are addressing critical issues such as climate change, health, medical research, and for some of us, we can even jump into action to develop vaccines in the middle of a pandemic. We can do really cool things really quickly, actively save people's lives, and we all have a part to play in that. What we do know is that we can't do that alone. So I think you're going to hear during my talk a lot that it's about people and collaboration that are our keys to success. By advancing eResearch infrastructure, we focus on our people. It's the most important thing. And so that's why, like I said, we engage with partners and collaborators all around the world. It's across a range of disciplines, expertise, computational areas, interests. We take a lot of best practices from a lot of groups of organisations and people to get the work done. Okay, so this talk will cover 3 of Pawsey's focus areas when it comes to advancing eResearch infrastructure. And that's our best practices, which I've kind of overviewed already, building an accessible and inclusive supercomputing centre, and how do we embrace and advance eResearch infrastructure in general. So let's start with our best practices. Yep, let's start with our best practices. So a cornerstone of our approach has been an inclusive and thorough procurement process. By engaging in our key science domain users early on in the process, we ensured that our infrastructure not only met the current needs of their research, but it was also poised for future demands as well. So when we went through our procurement process, for example, the rise of AI and generative AI wasn't a thing, but we still had a bit of a foresight to know that our GPU capabilities would be really important. And so now, a couple of years later, our researchers have been able to use our GPUs, and they're now exploring the age of AI as well. And they're doing some really cool things with our AMD GPUs, where AI is traditionally on NVIDIA GPUs, and now we're figuring out how we can port onto AMD. So now Pawsey, our supercomputing specialists, are doing a couple of world-first things that we probably wouldn't have known we could do before. And that's just through conversations with people, seeing what the research is needed, and then figuring out how we can do that. So this approach helped our decision making. And so, for example, our CPUs and GPU capabilities were based on some in-depth studies and that consultation that I mentioned with our research community. Calculations, extensive maths was gone into this to figure out what our efficiencies would be when deploying our infrastructure, as well as extensive user consultation as well. And so our approach to this wasn't just about fulfilling every single wish from the community that we can't grant that, right? Like, it's not feasible. So it was more about guiding our procurement to hear everybody and then fulfilling the widest array of research needs effectively, and then seeing how we can solve the rest as well, because usually there is a way. So this helped us make our informed decisions, helped with our choices, and also helped us to take some risks, because the technology that we procured at the time didn't exist when we went through this process. So it was taking risks on a few of the promises on technology that was not yet globally available. And we were able to take these risks because we knew what our people wanted. And so we could take that risk and then know that we're going to achieve this and we're going to be able to deploy it as well. We also had a range of committees that we consulted with to ensure that the right decisions were being made across all levels. So this included a user reference group, a technical committee, and a financial committee, and a procurement board that consulted directly with our board, as well as a few other reference groups as well. And so when we went through the tendering process, it was these groups that did blind reviews of the responses, so that we weren't necessarily purchasing the cheapest system or the most powerful system, but we were getting the best system based on our user, our technical, and our financial requirements. And so it was also really important for us in this process to choose a vendor that considered themselves partners in this and not just a vendor. So we wanted someone who had a vested interest in our scientific outcomes as a research community as a whole, and then have a collaborative mindset going forward as well. And then by doing this, instead of asking them for a technical solution with hardware, we posed them challenges. So we collated a lot of information from our communities, like I said, through consultation. We're able to form some key challenges and outcomes that we wanted to achieve from our procurement, and then pose that to our vendors. That's a very simplistic approach, summary of the tendering process. It was a lot more complicated than that, but that is what we tried to do, essentially, in its essence. And then, of course, engaging with our community, like I've said before, was critical in our procurement process. So not only hearing about their requirements, but then developing these requirements into training, documentation, and support, even before they migrated onto the supercomputers. Before the supercomputers were deployed. And so what we were able to do then was really speed up the migration when the supercomputers were deployed on the floor. So because we had all of this in place, we had extensively trained our users already, the migration from Magnus, our previous supercomputer, onto Setonix only took 3 months. Whereas when we migrated onto Magnus from our even more legacy supercomputers, it took 18 months. And so we were really able to learn from the refresh that we did about 6 or 7 years ago. We learned from it, we consulted again heavily, and then we're able to really deliver a smoothish migration across to our new systems. And so yeah, that was, again, research, consultation with our vendors because they had information about the technology, consultation with the community, making sure we were still doing what they wanted, extensive training and extensive documentation, and a really nice growing YouTube channel with a lot of videos on it as well, training videos. Okay, and so through this change management program with our capital refresh, we were able to raise about $3 million and put it towards Pawsey's PACER program. So the PACER program is Pawsey's Centre for Extreme Scale Readiness, and the goal of this program was to prepare our computational researchers for this next era of supercomputing. It was a technology that has never been seen before, and so we needed to somehow prepare them for that. So the focus on PACER was their extreme scale research. So being able to now scale up from a smaller system that they had before to a system that's now 30 times more powerful. And so we could do that through their algorithm design, code optimization, application, and workflow readiness. And so they used our infrastructure. We deployed Cetonix in 2 phases. So they started working on our initial phase to facilitate their research and starting to, again, produce some really world-class outcomes and reproduce that in their communities. I think that was the most important thing. So we had 10 projects that kicked off a 3-year program. But the real goal there was that they take this back to all of their research communities, and that filters down in their training and education, and then all of those communities can then take advantage and use these supercomputers. So like I said, it's designed as a 3-year partnership, and that partnership was with Pawsey, the research community, and our vendors as well. They were heavily involved in PACER and the training and education. 5 minutes already. Oh no.
Just talk really fast.
Oh God, okay. And okay, so we managed to achieve some really cool things. So like porting from CPUs to GPUs were resulting in a 25 times speed up on their time steps. They optimized their codes to be 6 times more efficient on GPUs. Some of their teams achieved a 25% performance improvement over the course of the hackathons as well. So we had some really cool outcomes. Those are some of the outcomes that... Oh, I've been thrown now. Those are some of the outcomes out of many that has now trickled into our research community. Okay, this slide is something that I'm definitely going to continue on. So it's all about, like I've said a million times now, collaboration, community, right? Equity, diversity, and inclusion is something that's really important to us at Pawsey. It's been changing over the last few years, but we've actively been working really hard in this space. So I am a part of Pawsey's D&I committee. I am a co-founder along with some of my colleagues here on the Women in HPC community for Australasia. And like I said, without people, you cannot achieve what you want to achieve. You cannot have success without a diverse group of people, without diverse thought as well. So that QR code leads to a video that is from some of our people talking about Pawsey, talking about the importance of diversity, equity, and inclusivity. Load it up, but don't all play it right now. The next slide is just a little bit about our chapter that Jana mentioned before as well. That QR code will lead you to, I don't know if my head's in your way. I'm not that tall. That QR code will lead you to join our community, and Jana has given me this bum bag. It's a Women in HPC bum bag. It's going to be a part of a prize pack that we're going to send out to you. So we can see the timestamps of people who join our community this week, and then we will send out a prize package that's more than the bum bag. We've got cute stuffed toys, stickers, and all sorts of things. But the key message is to join the community. You don't have to be a woman. It's Women Plus, because we want to create a safe and open space for all of us to come together. So please join. And we'll see you on our Slack channels. It's really active. We have informal fortnightly sessions and do some cool stuff. But diversity, equity, inclusivity, collaboration, and community, that's what today is all about. That's how you can advance your eResearch infrastructures. And we're holding an event in 2 weeks at SC Asia, Supercomputing Asia. You don't have to be a part of that conference to join our networking night. It's fun. It's just drinks. It's nothing formal. Come for free drinks, come for free food, and chat to people. I can't talk about the rest of the stuff, but it's all about people and doing the right thing. So I think I've covered a lot already. But like I said, the key takeaways is collaboration, consultation, people, diversity, equity, and inclusivity. This is the traumatic brain injury that I was talking about before. We're now using our systems across Australia's health network. We're doing real-time predictions on traumatic brain injuries before they occur, saving literally thousands of lives a year. The doctors here are using our cloud service for their real-time analytics with 90% accuracy to predict traumas before they occur, so then doctors can swoop in, act, and save lives. This is quantum computing. We're doing quantum computing stuff. We're exploring the space. We're trying to pioneer the field, or just at least set some pathways in the field so that researchers can now start exploring in quantum computing. And then when it really kicks off with edge devices and those sorts of things, we'll be ready. And then finally, we've got a really cool case study on climate science, our climate science initiative, changing the resolutions from about a 200 square resolution on a map down to a 4 kilometre square resolution. So instead of looking at climate change at a region, you can look at it at a very local level. It takes into consideration the local environments as well. So then you can now predict from until, I think they're doing predictions until the year 2100 on what that area will look like. And they're doing 2 extra models of predictions as well that has never been done before on different scenarios as well. So one of them is like, yeah, we didn't hit 1.5 degrees. The world is going to be great. Or, oh shit, we really, sorry, I can't say that. It's like, oh no, we went past 2.5 and everyone's going to burn. Cool different scenarios, and that's working with a few governments and researchers across Australia as well. And I have hit time. I've overhit time.
So you actually nailed it. I don't know if it's working. All right, we actually have time for 1 or 2 quick questions.
Awesome. Cool.
Turns out you could talk slightly slower. Here we go.
Hi, I'm not super familiar with what makes computers green. Can you say more about how you achieved the 4th greenest supercomputer in the world?
Yeah, absolutely. So you can do it in a few ways. So you could use renewable energy for some things, and then you can be efficient in the way that you use the computers for another thing. So using renewables, for example, we draw we draw water from an aquifer underneath Pawsey, and that water is pushed through our computers with fans to cool our systems. And then that is then injected back down into the aquifer quite far away, and then it replenishes the aquifer as well. So that's a really neat way to cool our supercomputers without massive air conditioning bills. The really cool thing from that was we did some studies to ensure that we weren't disrupting the environment in the aquifer. Not only did we find that the environment was thriving, we actually discovered 6 new species of stygofauna as well. So that was really, really cool. Yeah, that was a nice little, cool. The side of our building is also covered in solar panels. The side and the top of our building is also covered in solar panels, and that slightly offsets the cost of a power bill. The other thing that you can do, and that was really important in those calculations that I talked about when getting CPU and GPU systems, the more efficiently you can run your code, the less your computer is going to be used. And so that can really bring down our power bill. So some of our staff and researchers work together to write a paper on an accountability model for using a supercomputer. So we've calculated what those costs will be and how it works to run a supercomputer at a minimal cost. And then we do, through our extensive training programs, a big part of it is helping researchers optimize their code. So porting from CPUs to GPUs is one thing. GPUs are very powerful. They use up more power, but the amount of the multiplier in terms of their computational power is greater than the consumption of power. So helping them optimize their code, porting to GPUs when they can, and just generally being more efficient. Yeah, thanks.
All right,
I think there are other things as well. But
we only have time for 1 question. All right,
okay.
Let us thank our speaker. All right, so our next speaker is Aaron from REANNZ. And I don't know what we're going to talk about because I haven't got my piece of paper, so take it away.
Okay, I am here to talk about sort of making disaster-resistant infrastructure. It's actually more generalised to, all-important data infrastructure. I added eResearch there into the title to get it past the programming committee, and here I am, suckers. I assume we all sort of know who REANNZ is, and because I've got many slides, I'm kind of going to skip over these a little bit, but we run a national network. This is actually very out of date. Last year we did a full optical network refresh, so now we are running a optical provided by Vodafone or REANNZ now on their Sienna optical platform. So we run up and down the country. We provide connectivity to a bunch of different people. I've told our engagement team that we're not to bring on any more members because we can't fit anyone else onto the slide. And we also provide connectivity to sort of our counterparts across the world. That's connectivity and collaboration as well. So to the actual topic of the presentation, I have sort of been reading the news occasionally, and I've seen a lot of references to resilience, and in particular, government wanting or pushing for resilience on in New Zealand infrastructure. And I went and did a bit of research because I wasn't really sure what was happening here, and what I discovered actually really surprised me. So apparently, we have earthquakes in New Zealand. In fact, there's a reasonable chance, some statistics there from GeoNet, that we will have another reasonably big earthquake within the next decade. Actually, that was from 2017, so we've got 3 years left. Not only that, but we have extreme weather. I actually missed Cyclone Gabrielle because I had COVID that day, actually. I was home playing on my Xbox and just kind of going, oh, there's quite a lot of rain outside. We did have some issues from Cyclone Gabrielle. I'll just quickly say, because I've got it up there, we're getting a lot more extreme weather, as I'm sure we've all noticed, and that's probably only going to get worse as climate change increases. So we actually did have a few issues during Cyclone Gabrielle, but as I said, I actually wasn't paying any attention. I was playing Xbox and I wasn't paying any attention to Slack because I had COVID. We had 8 different fibre breaks on this path. It took about 2 weeks, I think, to repair all of them. Fortunately, we had another path. But we also did, this occurred around the same time as we were about to start the migration onto the REANNZ optical platform. And so our team, without me, like I say, playing Xbox, our team went and talked to REANNZ and actually expedited pulling up one of our new paths. So that actually gave us a path through New Plymouth, far away from the East Coast, to give us a bit more resiliency, because the last thing we wanted to do was get a fault on this other path and lose everything south of basically Napier. Well, actually, no, technically south of Rotorua. I added this picture here because this is actually Chorus rolling out some new fibre. They just laid it along farmland to get it out to Gisborne, to get Gisborne back connected up. So I thought that was pretty cool, and I was a bit upset they didn't ask me to go in their helicopter. We have other problems as well. This photo here is from one of our suppliers. You can probably see there's some ducting there. That's actually our fibre that's just ended up in the river. That took a little while to repair. It's a bit unsafe as well to get in there really quickly. So, look, we certainly had some wildlife, some rats eat through some of our fibres at one point as well. And yes, and then there is the biggest disaster of them all, and that is humans. And we all make mistakes, we all do dumb stuff, and I wanted to find a picture. There was something that happened in Tauranga back in like 2017 or something, where someone put an auger through a fibre. When it does that, it wraps it all around and then it splinters the fibre for like kilometres on either side. Takes a very long time to fix it, and it's very, very expensive to do so. But I couldn't find that picture because it was back in 2017. So I just want to be really clear. Things don't always go well, and we have to deal with that. Now, because this is a research conference, I wanted to come with some facts and figures, but unfortunately, I am a hack and a fraud, so this is all I was able to come up with. You can't actually read any of it because I do most of my communication via computer and I can't write anymore. But what this is trying to tell you is I can never offer you 100% availability. If you give me, and you can't really tell because it kind of looks like it's saying bow, but that's an infinity sign at the top there. If you gave me infinite money, I can still offer you maybe 9 nines of availability, potentially. Infinite money and the entire workforce on the planet. So we don't even bother going for 100% availability, and we have to accept that. And once we do, that actually makes our jobs a lot easier. So this is sort of the most important slide in the whole deck. Basically, as you're sort of looking at your infrastructure, these are the questions you need to be asking. Firstly, what's the cost of an outage? Is the cost of the outage, revenue, productivity, data, reputational damage, is the cost less than the cost of actually implementing the mitigations to give yourself higher availability? If it is, don't bother. Just take the hit and move on. But moving on there, what's the risk of failure of each component? The network or your entire end-to-end system, your entire end-to-end sort of data infrastructure is only as strong as your weakest link. So find your weakest link and fix that up. What are your single points of failure? Do redundant components have shared fate? This is things like power, or if you decide to put your firewall into an HA cluster, you're creating shared fate at that point. What are the chances of unrelated simultaneous failures? Usually it's really low, and being able to say that is actually a good thing. And in the end, is any risk that you have left acceptable? If it's not, you're going to have to spend more money on the problem. And the really important thing for us as engineers is to get someone above us to sign off on that risk. So I just wanted to go through the most common causes of outages. The first one is planned work. You have to do it because if you don't, then all of the other outages become way more likely. Fortunately, by sort of going through the steps to mitigate the rest of the types of outages, you actually mitigate any impact of planned work as well, which is pretty handy. So the first thing and the most common cause after planned work, I think, is human error. I may be sort of skewing the statistics there because I still have write access to the network. But the best solution to actually mitigating issues with human error and, in fact, software bugs is by building really simple, really repeatable network infrastructure components. So don't build everything bespoke. Figure out what you've done before, really standardize it, really document it. Here's the behavior, here's what we expect, and then reuse that over and over and over again. If you're not using different parts of the code base, then there's less to go wrong for software bugs. If people understand one thing and you're using it 500 times, they understand 500 things. The fourth most common is power outages. If you haven't got your infrastructure, server, whatever it is, on a UPS, and ideally backed by the generator, there's no point doing anything else because this is going to be your biggest cause of outages. If you can't do both, batteries, putting it on UPS is actually better than putting it on generator because the most common sorts of power outages are just very quick ones, as we found out in the office over the last couple of months. Fiber cuts, they're kind of more common than you expect, particularly for me, but that's because I'm working in networks, and so I see it all the time. Every week we've got another fiber cut or something that we're having to deal with. So 2 connections in, fully diverse, basically remove your shared fate there, and any single fiber cut won't affect you anymore. The next one is hardware failure. Happens not often, but not terribly often. But your solution to that is, run 2 devices with 2 connections into them. So here's your gold standard. Basically, you want to build all of that, and then do it twice in different regions, different parts of the country. We have our services infrastructure in Wellington and Hamilton, but there's plenty of data centres around. Take your pick, but ideally take your pick of the ones that we already have connectivity into it. It makes our job easier. You don't actually, if you do multi-region is actually the most important thing you can do. It is the easiest thing. You don't need any of the rest of this, really, if you do multi-region. Multi-region takes you from 99% availability to 99.99% availability just by being multi-region, because you've removed all shared fate, you've removed all potential for simultaneous failures, and then you just have the really low chance of coincidental failure. But adding all of that, you take it to 4 nines, 5 nines, 6 nines of availability by really doing the gold standard. And I did actually miss one, and I put it at the bottom there. It's probably not at the bottom, but it made the flow of the presentation easier, is upstream supplier failure. Now, I'm feeling a bit called out right now because I am the upstream supplier in a lot of instances. And so I just wanted to talk a little bit about some of the work that we do to finish off to actually improve the resiliency of our own infrastructure, which in turn improves the resiliency of your infrastructure. So here's something that we've sort of been looking at over the last little while. We've been looking at the South Island, in particular talking to Wallace, because way down here is University of Otago. And there's a couple of risks in that area. The first one is risk of earthquake in Christchurch. It's actually lower risk than, well, by all accounts, from what I read, it's actually a relatively low risk that we're going to get another big one in Christchurch. But it's happened before, it could happen again, and we have both of our fibres coming into the city pretty close, within probably 4 kilometres or something of each other. So there's a bit of a risk there with a large-scale event, which we've definitely experienced before. There is actually a second risk, and it's actually kind of a bigger risk. We sort of, get a little bit sweaty during winter when the rains are coming down on the South Island, because these rivers that come off of the Alps actually get really, really high. And in the Rangitata, and I think further north on the Rakaia, although the Rakaia River, I think I'm getting that one right, is a bit less of a concern. I think it floods its banks less often. But certainly in the Rangitata River, we often see bridge washouts and floods around as it goes over its banks. And this, because the fibre goes over those bridges, they get washed out, we lose our connectivity. So if we end up with, for example, one bridge go down, all the bits and pieces of it go downstream, take out the other bridge, we lose everything south of that, which includes, Dunedin and Invercargill. 5 minutes, I'm going quick. And, obviously we don't want that to fail. We've got University of Otago's main campus there. We've got Otago Poly, a number of CRIs, and also SIT down in Invercargill. So, we care about this. And so fortunately, Crown Infrastructure Partners, so the government has invested in a new cable that goes along the west coast, alongside Chorus. Up there, so bypasses all of that. It's on the other side of the Alps, so hopefully your weather systems will be a bit split. And you can head up all the way to Nelson and then across to Wellington. So we've actually turned this on Wednesday, so we've updated the weather map. There it is there. We've turned this on as a bypass of Christchurch and all of those risks. It's only 10 gig as opposed to the 100 gig that we typically run down that part of the country. But in the event of a failure, I'm sure Wallace will be happier to have 10 gig than no gigs. And that's it from me.
All right, I can confidently say we do have time for questions.
Hey, when fibre splits and you have the splintering, and how do you fix that?
Well, I don't. I've got people for that. Basically, what you have to do is you go all the way back to either side to where it's not broken anymore, you slice it and you splice new fibre in. Now you have to have quite expensive splicing equipment to do this, because you're talking about tiny little fibres, kind of thinner than a human hair that you're having to align like this and then fuse together so that the light can continue to penetrate through the fibre cable. And so you're going to do that. Usually they're about 60 core, maybe 120 core cables, so you're having to do that 60 or 120 times at either side, and then you're running a whole new overlay between those two areas, which could be a couple of kilometres. Hopefully you don't have to dig up that entire time. You can usually just run a new cable through the conduit, so just pull it through, maybe using the old cable or some other specialised equipment. And but if you do what FX did in the early days and you direct bury it, you basically have to dig up the entire several kilometres to do that. We don't really do that anymore because it creates expenses later on.
All right, any other questions? Wallace, nothing from you? You're happy now? Yeah, all right, he's happy. All right, good. Excellent, excellent. All right, then that has actually got us back almost on time, so thank you very much. Next up is Mike Laverick from University of Auckland, who is going to talk to us about something that involves NASA, and that's the only thing I could remember.
Kia ora koutou. So my name's Mike Laverick. I'm one of those people you see lingering around from the Centre for eResearch at this conference. There's quite a few of us. And today I'm going to talk to you about a little project I've been working on for the past 4 years. It's got NASA in the title, which is probably why you're here. And my presentation is supporting the NASA New Zealand Remote Sensing Airborne Mission, Rongowai. So of course, what is Rongowai? It's actually a world-first mission to host a research remote sensing payload on a commercial passenger-carrying airplane. And it's flying over Aotearoa today, every day, as we speak. Maybe not as we speak, it could be landing. It's actually a collaboration between NASA, Air New Zealand, and the New Zealand Space Agency. The actual thing itself is this lovely little box here. It's about 30 kilograms of luggage. It sits near the black box underneath all of the aisle. You have to take the plane apart for about a month to put it there. There's an antenna on the top, antenna on the bottom, and it took 3 years worth of negotiation with the Civil Aviation Authority to be able to do it. Of course, the actual word Rongowai was gifted to the project. Rongo comes from the te reo Māori word to sense, hear, or feel, and wai, water. So as you've guessed, we sense water using this instrument. So how does it actually work? It uses a technology called GNSSR, Global Navigation Satellite System Reflectometry, or in layman's terms, we use GPS reflections off the surface of the Earth to infer some information about the surface of the Earth. GPS is all around us. It's how most of us navigate nowadays. If you're lucky, these GPS satellites broadcast their radio waves down to Earth, hits your phone. If you get a couple, you know where you are. More often than not, it misses any device, hits the surface of the Earth, bounces back off into space, and we make space pollution. But if you can capture those reflected radio waves, you can start to infer some surface properties. So if you measure your baseline signal straight from the satellite, measure a reflection with something that's in the air, like a plane or another satellite, you can get some cool properties. Of course, there's lots of GPS satellites in space. That's how GPS works. So you can measure multiple of these signals at once. And these signals will tell you about a point on the Earth known as a specular point. And it will give you some information about that. If you do it for multiple at once, you can get 4 different dots on the Earth. And of course, satellites move, planes move, and as they move, you form these lovely little tracks along the surface of the Earth where you can get some information about. For Rongowai, it looks like these lovely pink worms. That is a science term I've been using for 4 years when I made this visualization. Not many colors stand out on the Earth's map other than pink. And so all of these worms that you see are made up of hundreds and thousands of individual data points sampled every second as the plane flies. So Rongowai isn't the first plane to actually use this technology. It's the first plane. It's not the first use of this technology. It's actually the spiritual successor to a NASA mission called Cygnus, and it's trialing the next generation of GNSSR receivers for future NASA missions. What is Cygnus? Cygnus is a cyclone global navigation satellite system. Basically, it's 8 microsatellites orbiting the equator, and those are used, using this technology, to map out and track cyclones before they hit inland, try and give you a bit more information about how they form and how much damage they may do. Each one of these satellites can track about 4 reflections. Rongowai can do 10. But of course, that's what Cygnus has done, but what can Rongowai do? Well, Rongowai flies 5 to 10 times a day, every day, and is going to fly for the next 7 years until the plane is decommissioned. That makes a lot of data coming in all the time, even while I'm talking, unless it's in the air. But this data can be used for several things over New Zealand. It can measure soil moisture content, so we don't need to put thousands of in situ sensors out there with connections. We can just scan it from the sky. It can do wind speed over water, so we can start monitoring wind patterns over the Cook Strait, for instance. It can measure and monitor and assess the ongoing impact of flooding and inundation events. I don't need to talk more about that. And of course, building this up over time with these 5 to 10 flights a day, every month for the entire year, you can start building up bigger trend pictures of soil moisture and even start tracking coastal dynamics and shifts there. So you can do some pretty cool things with it, which is why I'm talking to you. Finally, who is involved in Rongowai? Of course, I mentioned we have NASA. I have stickers on all of my stuff now. It's great. The New Zealand Space Agency and Air New Zealand. But there's a few more partners involved. The University of Michigan and the Ohio State University were involved in developing the actual payload and the firmware that's on it, and I've been doing several firmware patches as we actually get into a year of the mission. And the bit you've all been waiting for, my logo, and Canterbury's. We actually have New Zealand involvement here to do the support and the science for this mission. So I've talked to you for a while and not actually got back to my point. Supporting the Rongowai mission. This is where I come in and what I've been doing for the last bit. So at the Centre for eResearch, lovely little selfie with the box when we one and only time I've been able to touch the box. We've been helping to basically make sure everything works with the project. So we've been responsible for the communications with the payload, data and server hosting once we get the data off it. We've been helping with some of the algorithm development and optimization so that it runs fast all the time, every day. And of course, automated pipelines. I don't want to SSH in 5 to 10 times a day to press a button. So given the nature of it all, we've made it as autonomous and robust as possible. So the rough sort of Rongowai data workflow is the plane's in the air. It tracks all of these specular points as all the satellites fly around, makes these lovely pink worms. On this bit over here, you can hopefully see, it's quite small, individual dots that make up all of those tracks. It's a resolution of about 200 meters in diameter, so it's about paddock-sized, but once they overlap with each other, you can push that resolution a little bit better. So it collects all its data while it's flying, and each one of those points has around 70 parameters that we can pull from it. Quite a few of them are actually 2D arrays of the data. That's per specular point, 20 per second. Typical flight's about an hour, so 3,600 times 20, 5 to 10 times a day. It gets crunchy real quick, but that's a lot of wealth of data that we can use. Collects all its data in the air, it lands, and just like every other passenger, turns on its mobile phone as soon as it lands and starts to try and communicate with us. So what it does is it takes all of that data in a unstructured bit stream to make it as compressed as possible to send over a cellular network, and it sends it flying into our Nectar Research Cloud. From there, we take that data, we structure it, we decode it and structure it into the actual ints and booleans and everything that we want. There's a lot of doubles in there. And once we've got that data, we can actually then start putting it into a telemetry dash health board to see if the payload's still alive. We can start making level 0 products, which is basically the net CDF file that bundles all that data for the flight. And once we've got that bundle, then we can start making nice, shiny science products that we can release to the community for researchers to start using. We've got the level 1 science products. They're now science ready to go. We've got that sorted, and we've got a year release that we released at the end of December that we have now sent over to one of the NASA portals, the PODAC, which is the ocean one. And that's now publicly available for anyone to download. No restrictions. Anyone can go get it. So of course that's summarized 4 years of work on one slide. It's always great to be able to do that with your work. Makes you feel good. So I'm going to go into the nitty-gritty details just a little bit to give you a flavor for why this took closer to 4 years to do. So communication with the payload. It's really easy. It turns on its phone. It tells us all the stuff. Voila. No, connecting with Rongowai isn't so easy. Once it's installed in the plane and gone under the seats, that's it done. It's not physically accessible. Air New Zealand needs to take a plane offline for a month to try and access it. So once it's gone, it's essentially a satellite. You can be within 1 meter of it if you get on the right plane, which today is anyone flying to Blenheim or Tauranga later today. If you're on those flights, you may be within 1 meter of Rongowai. But of course, with it being on a mobile network, it doesn't have a static IP. Every time it lands in a different place, it gets a different IP. We don't know how to talk to it. So we need Rongowai to talk to us every single time it lands. So it calls us home, sets up a reverse tunnel. We can then SSH through that tunnel while it exists. And of course, it flies 5 to 10 times a day, every day, and I don't want to do that manually. So we automate everything. We don't control the schedule of when this flies. Air New Zealand does, and Air New Zealand doesn't always control the schedule of when this thing flies. It runs on Air New Zealand time. Flights get delayed, flights are early. The connection that we may have while it's on the ground will suddenly disappear when it's taking off. The cellular network coverage isn't always great. Nelson. It's pretty good in most places. But the point is we don't have any real grasp of when and how long we can communicate with this for. So what we've done is we've made the data workflow super robust so that it will always try to download the data and it will double check whether it's downloaded it before it moves on to verifying it. And all of this whole cycle ensures that we don't delete any data off the box until we know we've got it. And that just ticks away all the time. Speaking of that, resilience and monitoring of the payload. It's designed to be self-sufficient and resilient because it's essentially a satellite. We're never going to touch it again. It has its own onboard telemetry and dashboards to self-diagnose. Has its own telemetry. We put that into dashboards. I made some shiny Cabana dashboards that are interactive. It's way more fiddly than it should be to do interactive Cabana dashboards. But we have lovely green lights that will turn on and go yellow or red if something's going horribly wrong. They don't. But we can also monitor like the temperature of various sensors on board. Each one of these dips are the aerial temperature sensors. As it flies, it gets pretty cold outside. And so we can use this to get a quick head count of the actual flights. It's nice to see it in data. You can zoom in, and this is on 1 second resolution for temperatures. And again, with currents and voltages so that we know what's happening on the box once it lands. If it doesn't talk to us, that's probably a sign something's gone worse. It's always talk to us. One of the good things is that Rongowai itself has storage redundancy in case of poor connection. It can build up several flights worth of data and dump them later. The major airport hubs have good enough signal that we can get through any bottleneck in practice. The server infrastructure itself also needs to be robust to a couple of outages, and it's got at least a month redundancy in every single virtual machine that we've got. So we won't lose data for a month, which gives us lots of time to panic and fix things. And then, of course, there's the pipeline performance of the algorithms. As I've been harping on, it flies 5 to 10 times a day, every day, which means ideally we want these pipelines that generate the data to have at least a one-to-one real time. If we gather an hour of data, we want to process that less than an hour so that we don't get a backlog. The science algorithms are developed by researchers. I'm a former researcher, so I'm going to say this. They're not always as optimized as they could be. So we spent a while optimizing these to push these down to faster than real time. And this also includes if we want to reprocess a year's worth of data as the algorithms get developed for this world-first mission. We've now got it performant enough that we can implement a near real time so that once the flight lands, in less than a 30-minute turnaround, we can have a science-ready product of what the plane saw as it flew over an area. For instance, a flooded area. Workflow's not quite in place yet, but the capability is there. So as a summary of what we've done to date, and final slide, I've got a lovely map of Aotearoa here. This is the coverage that we have from December 2022, and it shows the signal strength, which will be more or less a direct proxy for the soil moisture in New Zealand. And so you can start measuring this lovely swath of New Zealand here. We've got quite a few more months than that now. So for some numbers, we've done over 3,200 flights since it started. It's about 275 gig of bits streamed straight from the plane to the servers. It's unpacked to about getting close to 0.5 terabyte for this mission now. We've done about 20 in-place payload firmware updates, firmware and software, and it still talks to us. It's robust. We haven't bricked it yet. And it even survived a lightning strike within its first month or two, which had us a little worried and took the plane offline for 3 weeks. In practice, we've had a couple of network outages and things, and realistically, we have at least a few months storage before we'd lose any data on board or in any of the virtual machines. If we put everything up to science produce maximum, 1 month. And my proudest bit is the pipelines, the communication with the actual payload ran for about 6 months straight without me having to do anything with the server until it didn't, which was about December last year, just before I went on holiday. Reboot service, running again. Yes. So yeah, thanks for listening. Lovely QR code here and a horrible long URL. This is the actual data release that we have now. You can actually go get this year's worth of data and start playing around with it. If you want some more information, get in touch, and then we can put you in touch with the researchers to get you all the right information on how to use it. Thank you.
Thank you.
And you have left yourself enough time for questions, so I will open the floor. But first I will say that was freaking awesome. So thank you. Right, questions. I'm sure there are some. Yeah.
Oh, what next? So we finally got the science-ready products, but they're only the level 1 tier. What we want to then do, and by we I mean the researchers, is to start creating the algorithms to produce gridded soil moisture products, so easier ones for people to use. We've got links with various farmers who are doing regenerative practices, and so we want to be able to provide them with easy, almost CSV level formats of this is what your soil moisture looks like over this period of time, how your practices are actually working or not working. So now that we've got the actual data there, the researchers are going to start producing the easy, digestible, useful content for everyone, industry, research, whoever needs it.
Oh man, everywhere.
So in that vein, you have flights that take slightly different paths with satellites that are in slightly different positions. Do you actually get enough repeated data to actually get like a resolution over time? Like, is it if they have the same flight path every day, do you every 10 days get the same data points, or how does that work?
There's quite a bit of variability in the flight paths, and we've got zero control. We can't tell them to get this nice little image here. The flight goes where New Zealand wants it to. In practice, we do start building up a nice amount of coverage. The flight routes themselves, while they do deviate a little bit, they tend to go over the same regions, and in practice we've seen that the specular points do cover more or less the same bits. We've also got per specular point, it's a 200-meter diameter, so it's a big enough paintbrush that you will touch nearby, and then you can always try to rely on the assumption that if it's near enough, then it's maybe the same behavior. But yeah, in practice, from what we've seen, yes, it does, especially closer to the airports, you do cover the same areas often enough. Which airports it goes to on a given day is a bit more sporadic. The Cook Strait gets a lot of attention from what I've seen, because it keeps going to Nelson and has no signal.
I have a question. So in Australia, where I'm from, we are highly susceptible to bushfires. So what's the accessibility? Like you have that, you're trying to do like that one-to-one processing. What's then the access to researchers for that data, or institutions or government or firefighters and so on?
Yeah. At the minute, we've got about a day and a half delay before it's published to the NASA archive. The researchers are currently working on collaborating with an external company to fire the data across ASAP to then get it produced within this half-an-hour window. The idea being that then they can start linking that back into government and other key people who need to use it. I don't know yet, but it's certainly flying, or it's certainly in action at the minute to try and get that kind of quick response.
Have you had any other nations' aeroplanes interested?
Not that I know of. It's a domestic plane because you can't just put a receiver on a plane and fly it over any other country. They tend to not enjoy mysterious sensors put on it. However, we are now, I say we, it's now being costed up to reproduce and create a second one. The idea being that we have 19 other of these aircrafts in the fleet that, without any further CAA approval, we can install 19 more over New Zealand, which then dramatically bumps up your temporal coverage of the area. So other countries, not sure. I think it's going to be a harder precedent to do, but expanding Air New Zealand's fleet with them is probably the next step in that vein, and it's starting to get the ball rolling with additional ones. Just super cool.
I'm going to ask a question first. So that was on an ATR, right? Rather than a jet?
It was on not a jet, it's a Q300.
Okay, sorry, yeah, but propellers rather.
Yeah.
How many other countries are flying propeller planes around? Like, think about the US, I don't know. Did they use
Quite
a lot,
few.
right?
So the main issue you've got is it's certified to go on this specific plane by the New Zealand Civil Aviation Authority. Anytime you want to put it on a slightly different plane, no matter how similar it might be, it has to go through that process again. New Zealand's one of the more innovative civil aviation authorities, which is why it's gone ahead in the first place. And so there's a lot more barrier to getting this done in other countries, but New Zealand's setting the precedence.
So the frequencies used for that one, they're the ones that are available. It's a natural resource, the GPS signals, and the previous ones. So is Starlink a useful one, or is that not one that's going to pick up the water? Because they've got a pile of different ones, and now that's a free resource. Is they're looking at any of the other free ones using GPS? Does it include the GLONASS ones?
GLONASS is on the radar, but for them to include. They just need to actually get the firmware update going, which you have to be very careful with all of our firmware updates. So the plan is to expand it out to more global navigation system. I think the frequencies might be the tricky parts, and making sure you've got an instrument that can pick up all the frequencies. And I'm sure Starlink would love hearing that people listen into them.
It reflects it's the reflected glory.
Yeah. So no, not that I'm aware of for Starlink, certainly for the rest of the GNS, the GLONASS, etc. They want to do that, but it's a time resource issue now.